A'udhu billahi minash shaitanir rajim. Bismillahir Rahmanir Rahim. Dear students, today we have a theorem. If the class of the upper sum, capital S, and the class of the lower sum, small s, respectively, for all the possible partition J is equal to JLB of the capital S, upper sums, and I is equal to LUB of the lower sum, small s, then prove that J must be greater or equal to I. Proof: since J is equal to JLB of the upper sums, or J is equal to JLB of the capital S, and I is equal to LUB of the lower sum, or I is equal to LUB of the small s. So from the definition of J, as J is the JLB of the upper sum, so J must be less than or equal to capital S. And also from the definition of the LUB, I must be greater or equal to small s. And also we know that from the previous lecture that yk minus 1 m of ek is less than or equal to yk m of ek, where yk minus 1 yk belongs to the partition sets y0, the set y0, y1, y2, dash 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 yn, such that alpha is equal to y0 less than y1 less than y2 dash 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 less than yk minus 1 less than yk less than dash 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 less than yn minus 1 less than yn, which is equal to beta. It means that this alpha is equal to y0 is the starting interval point, and yn is equal to beta, this is the last interval point on y-axis. That is, fx is bounded in the range alpha and beta close interval, because all the values of the function must be greater or equal to alpha and must be less than or equal to beta, and these are for the function on y-axis. Then taking over the sum, summation k is equal to 1 up to n yk minus 1 m of ek less than or equal to summation k is equal to 1 up to n yk m of ek. This summation for the yk minus 1, this shows small s, and yk summation, this shows capital S. But it is true for every partitions, and J is also an upper sum because J is equal to GLB of the upper sum. So it means that J is equal to capital S, and I is the lower sum as I is equal to LUB of the small s. So for a particular partition set, so I must be less than or equal to J, or J must be greater or equal to I, as small s is less than or equal to capital S. Therefore we can also write I less than or equal to J. Now we have next theorem which are the same as above. If S is an upper sum corresponding to a partition's small s is the lower sum corresponding to the same or the different partitions, then prove that small s is less than or equal to I is less than or equal to J, and J is less than or equal to capital S. Since I is equal to LUB of the small s and J is equal to GLB of the capital S, from the definition of LUB, I must be greater or equal to small s, and from the definition of the GLB, greatest lower bound, J must be less than or equal to capital S. Also for any partition set y0 dash comma y1 dash 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 yn, on the y-axis we have yk minus 1 m of ek is less than or equal to yk m of ek. Taking over the sum, summation k is equal to 1 up to n yk minus 1 m of ek less than or equal to summation k is equal to 1 up to n yk m of ek. This yk minus 1 summation represents small s, and summation of yk represents the capital S. And we know that I and j are the lower sum and the upper sum. I represents the lower sum and j represents the upper sum for a particular partitions. And from the above theorem, we write it, we prove it, I is less than or equal to j. Thus, s is less than or equal to I, and I is less than or equal to j, and j is less than or equal to s. That is required.